Hey everyone! Today we're going to talk about radical polymerization, and this is actually the last topic we'll cover in this chapter. So polymerization is the process of adding smaller molecules together to create a really long chain, so a much bigger molecule. Now there are two types of polymerization. So the first type is condensation polymerization, and the other type is radical polymerization. Now, in condensation polymerization, when you join two molecules together, you typically lose like a water molecule or a methanol molecule in the process. So it's sort of like an elimination reaction in a way. But that means you do end up with some byproducts, which isn't always desirable because then you have to remove those byproducts. So you would have to, let's say, boil off any water that forms or maybe the methanol that forms. But radical polymerization doesn't have any waste, or rather, it doesn't have any byproducts. So let's just look at a general polymerization reaction. So first of all, you start with something called a monomer. Mono meaning one. So let's say we're starting with an alkene, and it has different alkyl groups surrounding it. Now, if we go through the polymerization process, so we'll just write polymerize. What we're going to see are repeating units of these carbons attached to different R groups. So this double bond becomes a single bond with those R groups all attached. And then that's going to connect to other groups that are the same. So we show that by drawing these brackets and kind of extending those outer bonds beyond the brackets. And the idea is that there's more of those groups on either side. So it's just a repeating unit over and over again. So you kind of get the idea. We just get this, really long chain. But I'm going to erase this so you can see how we symbolize that. And then we also put a little lowercase n off to the side on the bottom right, and that tells us the number of units that are repeating. So let's say we have 7 of these units that are all connected together. We would replace that n with a 7. So that just tells us the units that are repeating. Now, you can have small monomers, and small monomers polymers. Oh, I misspoke. You can have small polymers, which might be tens of monomers long. So you could have 10 monomers in a row, you could have 15, you could have 70 monomers in a row. Those are considered small polymers. But large polymers will have hundreds to thousands of monomers in a long row, all connected together. Now, we use polymers in everyday life. They're all around us all the time. So polymerization is a really useful reaction. Now, some of the polymers we use aren't great for the environment, but they're still useful for us day to day, as long as they're reusable, I guess. But let's look at a few of those. So the first one, we start with ethylene. So ethylene has hydrogens on either side. So this is our simplest alkene. And if we polymerize that, we end up with a polymer called polyethylene. So you might have heard of this before. And this is what makes up plastics. So plastics are made of a type of polyethylene. Another polymer that you might have used in your day-to-day life involves starting with a molecule called propylene. So this is an alkene with a methyl group on one side. Oh, porpylene. I think I was trying to write the word porpoise. Propylene, there we go. All right, so propylene, if it's polymerized, will make a series of repeating units where one of these carbons has a methyl group on it, and then the other substituents here are just hydrogens. We'll put brackets around that. So this is called polypropylene. And this is actually what's found in carpet fibers. It's also used in camping gear. So it's really, really durable. Okay, another type of polymer that you may have heard of is polystyrene or styrofoam. So to make polystyrene, we start with a molecule called styrene. So it's a benzene ring with two carbons coming off of it, and there is a double bond on the very end. So when we polymerize that, we get the following. And I'm going to abbreviate the benzene ring as pH. So pH is this over here. So it's the benzene ring with a carbon coming off of it there. The other carbon just has hydrogens on it. So this is, again, polystyrene, also known as styrofoam. And this is really difficult to recycle. So you might have noticed that you have to throw away styrofoam. You can't recycle it. So if you can avoid using styrofoam, that would be great for the environment. But it's hard to completely avoid it because it is used in, for instance, packing materials, and it's used a lot. Another one that you might have heard of is polyvinyl chloride, or PVC. So this is often used in piping or tubing. So you start with something called vinyl chloride. And it's called vinyl chloride because the chlorine is on a vinylic carbon, which is one of the carbons in the double bond. Now, if we polymerize that, we get the following repeating units where one carbon is bonded to a chlorine. Whoops, there we go. So again, this is called polyvinyl chloride, or PVC. So this is used in piping or tubing, and it's very, very durable. The last one that you might have heard of is called Ptfe or Teflon. So if you use non-stick cookware, you'll now know how to make it. So we start with a double bond, and each carbon has 2 fluorines attached. So this is called tetrafluoroethylene. And when we polymerize it, those 2 carbons are each bonded to 2 fluorines again. And we're just repeating that unit over and over. So polytetrafluoroethylene. And we abbreviate that Ptfe. So if you've ever wondered where some of these names come from, now you know. But again, the more common name for this is Teflon, and it's used in non-stick cookware. Now, Teflon is potentially hazardous if it starts to kind of flake off. So if you have a non-stick pan and you notice that some of the non-stick stuff is coming off, it's time to replace your pan because that stuff could potentially cause cancer. I remember one of the pans we had started to kind of chip, and I called it the cancer pan, and we stopped using it. But yeah, time to get new cookware if you see that chipping. Okay, so let's go over the mechanism for radical polymerization. So how do we actually form these products? So we are going to use a peroxide to start. So in our initiation step, we start with our peroxide, and that's going to homolytically cleave once we add some light or heat. And we form our 2 radicals. Now, let's just use ethylene as an example. So one of those radicals will react with ethylene, and the radical will form a bond using one of the pi bond electrons, and the other pi bond electron is going to just stay on the other carbon. So now we have a covalent bond between OR and one of the carbons that was in the double bond. The other carbon that was in the double bond has a single electron. Okay, so then in our next step, the propagation steps, that radical we just formed is going to react with another ethylene molecule. So we're going to couple them together there, and we're going to form another covalent bond. But this will still be a radical. So now we can add another ethylene molecule, do the same thing, and we're just going to do this over and over and over again until we get a super long chain. So we'll add more ethylene, and then it continues. Now, in the termination step, we're just going to cap off the very end of our polymer with another OR group. So what I'll do is, in order to symbolize that we have repeating units, I'm just going to put parentheses around this central part of the molecule. And I'm just going to put, however many units we have that are repeating. So maybe there's 100 of those, so I'd write 100 next to the parentheses. Maybe there's 1,000 of them, so I'd write 1,000 next to the parentheses. However many repeating units we have. Now, this is still a radical chain, so what we'll do to terminate the step is to use our other OR radical that was left over from our initiation. And we're just going to couple them together. Oops, I don't want to highlight that. And that will finish off our polymer, so it will stop reacting. Oh, my pen stopped working. There we go. Okay, so again, this is very similar to other radical mechanisms we looked at. You have your initiation step, so you're kind of starting off your radicals there, and then in the propagation steps, you just keep adding on more and more 2 carbon chains until you're done, and then in the termination step, you just cap off the end with your other OR group. Now, one thing that can happen is you can have side branching occur. So let's say you have one of your radical polymers here, so maybe you're 5 steps into the process, and maybe you have another polymer that looks like this. So what could happen is your radical can abstract a hydrogen from the polymer. So you end up with your terminated polymer plus a new radical. So this will be a secondary radical, depending on what type of polymer you added in. Then you can add in ethylene, and your new radical will form a bond with ethylene. And now you have a branch coming off of your polymer. So side branching does affect the physical properties of polymers. So for example, if you have a plastic bottle, that likely has side branching in it because it's more flexible than, let's say, the cap of a plastic bottle, which is inflexible. So side branching affects the physical properties. So it can also affect, for instance, density and other properties as well. Okay, so let's summarize the reactions that we talked about in this chapter. The first one is bromination of alkanes. So if you have an alkane, let's say this one, and you add Br2 and you use light to initiate it, we now know that bromine can add to the most substituted carbon in that alkane. We also talked about anti-Markovnikov addition of HBr. So if we start with this alkene and add HBr and peroxides, then we'll add bromine to the less substituted carbon on the double bond. And we went over that mechanism, so definitely know that mechanism going forward. And then finally, we talked about allylic bromination. So if we start with that same alkene that we drew above and we add N-bromosuccinimide, NBS, and light, we end up with the bromine attaching to the allylic position. So remember, the allylic position is right next to that double bond, so it's one carbon away from the double bond, and that's where bromine will add. But remember, in one of our examples, we talked about how if you have resonance, you can also end up with another type of product or a constitutional isomer. So watch out for resonance. Okay, so these are the three main reactions that you have to know for this chapter. So a little bit easier than the previous two chapters that we went over. And just have a general idea of polymerization. I don't expect you to really go over or draw a whole polymerization reaction, but just have a general sense of polymers. There might be some polymer questions on your homework, for instance. But otherwise, in the next chapter, we're going to go over synthesis problems. So we're going to take everything we learned in the first three chapters and we're going to put it all together in this next one. So I will see you then.